What exactly turns a perfectly healthy brain cell into a devastating tumor? Take a moment, let that question really sink in. Welcome to today's Explainer. We often think of cancer as this sudden, random, biological lightning strike. But the truth is, brain cancer isn't just a single isolated event. It's actually a perfect storm of converging factors. So let's dive right in and break this down.
Here's our roadmap for this explainer. We are going to start by looking at the genetic blueprint. Then we'll move into the external risk factors. And finally, we'll examine the cellular chain reaction that actually drives the disease.
All right, Section 1, the genetic blueprint. This is where the internal foundation of healthy cell growth control completely falls apart. Take a look at the glowing DNA right next to the developing tumor. You see, changes in our DNA sequence, whether they're inherited from our parents or acquired over our lifetime, act exactly like a faulty architectural blueprint. Instead of telling the body to build normally, these specific mutations instruct the brain cells to just divide uncontrollably. And that leads directly to the malignant transformation we commonly call a glioma. Now, the absolutely crucial point here is that specific genes are the culprits. Think of genes like TP53 and PTTN as the biological brakes for your cells. When they mutate, those brakes fail, and the cell totally loses its ability to suppress tumors. On the flip side, overactivation in a gene like EGFR acts like a stuck gas pedal, just promoting endless runaway cell division. Throw in IDH1, which starts producing abnormal metabolites, and ATRX, which completely disrupts genome stability, and suddenly the cell's entire control system just completely collapses. It's wild when you think about it. But how does this master blueprint actually break in the first place? Well, there are a few types of structural damage that can happen. We've got point mutations, which are basically just tiny little typos in the genetic code, but there are also massive, large-scale chromosomal deletions or amplifications. Then you have epigenetic modifications, which actually change how the genes are read by the body, and of course, dangerous gene fusions, like the BRAF fusion. It really just goes to show that our DNA is literally constantly under threat. And that leads us perfectly into Section 2, external risk factors. Let's shift gears from the internal genetic blueprint and look at the external triggers that can actually cause all these harmful mutations. Look at the risks circling the brain in this image. Environmental agents and ionizing radiation are physically assaulting our cells all the time. These are everyday exposures, or sometimes extreme ones, that can literally physically break our DNA strands. That physical break is exactly what initiates the perfect storm we're talking about today. We can break these external triggers down into two main categories. On the left, you've got the invisible dangers, ionizing radiation. Now, this comes from high doses of medical CT scans, nuclear exposure, or, believe it or not, even cosmic radiation from space travel. On the right side, we have chemical and environmental toxins. We're talking industrial solvents, pesticides, the harsh carcinogens found in tobacco smoke, and heavy metals like lead and arsenic. These things can induce severe neurotoxicity and totally wreck your DNA. Okay, let's move on to Section 3 to see how all of this builds up. This is the cellular chain reaction. It's the final stage where that faulty blueprint and those external triggers join forces to start the engine of carcinogenesis. So when those external factors finally hit the cell, it kicks off this incredibly toxic initiation phase. First, we get direct DNA damage, so we're talking lesions and physical strand breaks. Second, oxidative stress just floods the cell with reactive oxygen species, completely damaging proteins and lipids. Third, chronic inflammation kicks in, which releases pro-inflammatory cytokines. And fourth, epigenetic alterations step in to silence our absolutely vital tumor suppressor genes. Put it all together, and it creates a deeply toxic microenvironment that just perfectly feeds a growing tumor. The direct result of all that toxicity is cell cycle dysregulation. You see, normally, a cell has very strict checkpoints before it's allowed to divide. But here, there is a complete and total failure of the cell's internal control system. Critical checkpoints like the P53 pathway just completely break down. That leads to unchecked, rapid cellular replication. Like we said earlier, the biological brakes have just totally failed at this point. And once that tumor starts growing, it needs an immense amount of energy, which brings us to angiogenesis. The tumor cells, brilliantly, but honestly terrifyingly, start secreting factors like VEGF to promote the formation of brand new blood vessels. Think of it like the tumor building its very own dedicated supply lines. It literally tricks your body into feeding it the blood and nutrients it needs to keep expanding. It's a real game changer for the cancer. Finally, to survive permanently, the cancer develops apoptosis resistance. Now, usually, a heavily damaged cell undergoes programmed self-destruction for the good of the body, right? But mutations in specific genes, like BAX or caspases, allow these cancer cells to simply evade death entirely. They effectively disable the cell's natural self-destruct sequence, achieving this incredibly dangerous form of biological immortality.
So that brings us to our final thought for today. If we now understand the genetic blueprint, the environmental triggers, and the exact cellular engine that drives brain cancer, just how close are we to finally turning it off? That is exactly the question driving medical researchers all over the world right now. Thank you so much for joining me for this explainer. Keep questioning, and as always, keep learning.